In the several lecture segments of this topic, we'll deal with the two most important ideas in object-oriented design, the is-a relationship and polymorphism. Now, let's look now at the last few lines of vector test to illustrate an important relationship between subclasses and superclasses. Now, we create two margin vectors here, and we point v1 and v2 to them. And question one, look closely here. Do the types of the left and right hand sides of those assignments match? Returning from a pause, there's really no trick question here, it's pretty obvious. They don't match. We're assigning margin vectors into vector references. Right? v1 and v2 haven't been declared up here as originally vector references, and we're changing what they point to, by the way, to a margin vector instead of the original vectors that they did point to. So, can we do that? Yes, and this illustrates a critical concept. In fact, one of the critical concepts of object-oriented design. Any subclass object may be treated as though it were a superclass object. In particular, a superclass reference like v1 may point to a subclass object, a margin vector, in our case. Now, when you think about it, this makes some sense. A subclass like margin vector is guaranteed to have all the methods and members of its superclass, so it can handle all the method calls or member accesses that a superclass object could. In a sense, a margin vector is a vector with a few extra members like margin and methods like set margin, get margin, and then of course a redefined equals. And we could visualize that as down here with the v1 now pointing to an object that has a vector part and a margin vector part all in one subclass object. And so if a reference like v1 over here points to that object, we can still do with v1 all the things we could do with v1 if it pointed to just a vector. We just ignore the extra methods in margin vector and call only those for vector. The idea that a subclass object is a superclass object is central to object-oriented design, and it's used in almost every object-oriented design pattern. There isn't an object-oriented program of any significance that doesn't make use of this idea, usually in hundreds of places. And it's so common that OO designers usually run the words is-a together as a kind of emphatic single phrase like that. And so we speak of the is-a relationship between a subclass object and a superclass object. A margin vector is a vector. Now, as we'll see when we discuss object-oriented design patterns, the ability to use a subclass object in code that expects an object of its superclass provides remarkable design flexibility. The ability to use a margin vector where a vector is expected, for instance, provides such flexibility, especially when combined with the second major concept that we'll look at now, polymorphic methods. So right after we set up those two margin vectors in the code, we check them for equality, and then we print the result using printf's %b format specifier, by the way, for Boolean values. And notice, by the way, in this context that we did set margin to 3.0, which means that even though those are two different vectors, they are close enough to be considered equals according to the margin vector equals method. But they would not be close enough to be equals according to the vector equals method, which demands exact equality, of course. So here's the big question. Which equals will be called? We should consider that question very carefully. There are two lines of reasoning that seem possible. We've got this situation here, and one line of reasoning would say, option 1, it'll call the vector equals, because the compiler can't be smart enough to know the object is really a margin vector. v1 and v2 are vector references. The compiler has to translate that equals call into some sort of jump in the bytecode, and it decides where to jump for a method call based on the type of the reference. It's not smart enough to look at the prior lines and say, oh, I see you actually pointed v1 and v2 to some margin vectors over here, so I'll translate that call instead to a jump to margin vector equals. Even if it were that smart, those assignments, might have been made hundreds of lines earlier in a completely different part of the code, in a different method, and the vector references passed to us as parameters. You think the compiler is going to look that far back? Or to be really obnoxious, we could write code that you can see in the notes, and I'll drop down here in the diagram. We could have done something that assigned a random value into I. And then if it's 0, that would assign a random integer of 0 or 1. If it's 0, then we'll do margin vectors, and if it's 1, we'll do vectors, and then we'll print out the result of the equals method based on that call there. Now, your smart compiler has to guess which way the next int call is going to go before the program even runs, and translate the code into a jump to the right equals based on that. We could also run that code multiple times and have a different assignment each time we ran it, and we'd have to have a different equals called during runtime based on which way that if statement went. So obviously the only viable alternative is to use the type of the reference to determine which equals is called. Regardless of the actual type of the object, we can pass margin vectors to the vector.equals method, both as context object and explicit parameter. They've got x and y members and all that, but the equals behavior will be vectors, not margin vectors. Now that's argument 1. Here's argument 2. It will call the margin vector equals because doing so would be one of the most useful software design features in decades. It would be really great if it called margin vector equals, because that would mean we could customize the behavior of that equals call, right, based on what type of object, a vector or a margin vector, we point the references to. Indeed, if we had several different subclasses of vector, each with a different override of equals, then we could get a single piece of code that points to any of them via a vector reference, since all of them would be vectors, so to speak, and yet the right equals would get magically called. And the compiler doesn't have to be psychic to do this. What it could do is embed information directly in the objects to tell it which method to call. Each margin, or every margin vector object, would include some kind of hidden data indicating that the right equals is margin vector equals, and every vector object would include hidden data indicating that the right equals is vector equals, and every additional strange vector object would likewise have the information to point to its form of equals. So the compiler doesn't translate the equals call into a particular bytecode jump. Instead, it translates the call into bytecode that fetches that hidden data from the object and calls the indicated method. The decision wouldn't be made at all until the bytecode is run, by which time the right object will be there to be consulted. Even if you put the call in a loop and v1 or v2 point to different vector subclasses on each iteration, it would still work, calling whatever methods the current objects indicate. Now, as you can guess from the tone of the arguments, the truth is option 2. This behavior, in which the target object, not the type of the reference, determines which method is called, is the object-oriented language feature. Everything in object-oriented design builds on it. It looks kind of technical and obscure when you first learn about it, but it enables the kind of object swapping described in the first paragraph of that option 2 argument we just made, and that opens the door to all sorts of designs. We'll see plenty of examples of this idea in later segments, but for now we need a term for it. Calling a method based on the type of the object, not the type of the reference, is called polymorphism, and the method that behaves this way is said to be polymorphic, which is Latin for having many forms. And like other important concepts, polymorphism has several synonyms, all of which you should learn. It's also called runtime binding, because the decision on which equals method to call waits till the translated bytecode actually runs. And binding, by the way, is compiler speak for deciding what a name, like equals, means. It's also called dynamic binding for similar reasons. But all this doesn't mean that option 1 is useless. For one thing, it's faster than option 2, since it translates to a simple jump instead of a runtime consultation of the object. Sometimes that speed is essential, and we do without polymorphism for some methods. Option 1 is called compile time binding, or static binding. And that use of static, by the way, is different from the uses we've seen as a keyword. The term static crops up in a lot of places in computer science. Now, any practical object-oriented language lets you turn off polymorphism for selected methods for the sake of speed. Java doesn't explicitly let you do this, but you can give it a strong suggestion to do so by declaring the method final in the base class, as we do for getX and getY. I'll bring up Eclipse briefly here. As we do for getX and getY in vector. This declaration, the final, means don't allow any subclasses to override this method. Any attempt to override a final method will cause a compile error. If a method is never overridden, then there's never a choice between the superclass and subclass version, and polymorphism is moot. For such methods, the Java compiler will probably make the call statically bound, but a suggestion is the most you can make. So, in summary, if you override a method in a subclass, but point a superclass reference to the subclass object, then you get the subclass version of the method, because the subclass object has a table of information inside it, indicating what methods should be called for it, and the call is translated into code that consults that table. But if you make a method final, you are agreeing never to redefine it, and are suggesting to the compiler that the overhead of polymorphism is not needed. This makes sense for simple methods that you call a great deal, like getters.